I'm good. Hey, Professor, I had a quick question for you
Sure.
before
What's
lecture
up?
gets started.
Hmm.
So I know you might not know this, but I was just hoping you would. So I see on the class schedule for next semester's classes, there is EGME 541, which is, I think, a finite element analysis for engineers or something like that.
Yep.
Is that going to be a continuation of this class where we learn more advanced techniques with ANSYS, or are we going to be working out actual finite elements on paper and learning the theory behind what kind of goes on behind the scenes in a program like this?
Yeah, it's gonna be the second one. I mean, ultimately, it's gonna depend on who teaches it. Um, Although I think I'll probably be the most likely person that teaches it. Unless we have a part-time faculty that feels really strongly about it. So generally, the way our department schedules is so they schedule the part-time faculty first, just because they have a little bit less flexibility in their schedules because a lot of them are working other jobs at the same time. And so they usually kind of get first dibs on what they want to teach, and then we're assigned stuff after that. But no one's really taught finite element stuff except for me for the last couple of years, and so it's likely going to be me. And my plan for the class is yeah, we're going to be diving a lot more into the theory, working things out on paper, and actually implementing finite element code as well. And so the final project for that class is, we're actually going to be writing a finite element code from scratch in MATLAB. Yeah.
Okay, so there's going to be no ANSYS then in that class.
There's going to be a little bit, there'll be a little bit of ANSYS, but it'll be mostly a repeat of what you've seen in this class already. Just because some people are taking 541 kind of just fresh, without any prior finite elements. And so, ANSYS I know is an important skill to take to the workplace. And so I use it a little bit, but probably only about, I'd say maybe 20%, less than 20% of what we're doing in this class.
Okay. Okay. Alrighty. Thanks,
Mm-hmm.
Professor. And you're saying it's going to be most likely you that teaches it?
Most likely, yes, at this point. But I don't know how the staffing is like for the part-time faculty. And so I know for this semester and next one, the department's having some trouble with staffing just because there's just a lot of shortages all around. And so if they hire someone new that feels really strong with finite elements, they might give it to him or her. But as of now, then I'm probably the most likely one. Yeah.
Okay, sounds good. Thanks.
Mm-hmm. All right, it's 5:30, so let's go ahead and get started today. All right, good evening, everyone. How's everyone doing today?
Good.
Good, good. Yeah, good to hear. All right, so today the plan is we're going to continue our lecture notes on advanced meshing, okay? But before we do that, I did promise you guys I would show you some features in ANSYS, and I did actually look them up before the class today. And so there are three things that I want to show you that hopefully will be useful to you for your projects. Okay, but hopefully it shouldn't take too long, just because each of these tutorials are pretty quick. But hopefully you guys can use them in your projects, and it'll just be helpful to you in general. Okay. All right. So are there any questions before we get started today? Okay. All right, so let me go over quickly how to or the three things that we're going to go over in ANSYS, just so that we can have it written down before we actually start. All right, and so the first tutorial that we're going to look at is to how to basically split a surface. Okay, and the reason you would want to do this is to create a smaller region or an additional region for you to apply boundary condition. Okay. Okay. All right, so that's the first one. And the second one that we're going to learn is how to split a model itself, right? And so I was asked this by someone who's doing the bearing housing one. And so one way that you can approach this is to say that I want to just by taking advantage of the symmetry in the system, let's go ahead and cut the model down the middle, take out one side, and then just focus on just the other side. Okay. Right. And the third feature that we're going to go over today is how to do section planes within ANSYS Mechanical. Right. And so in case you're doing something like the globe valve, and you want to look on the interior of the model, and you want to do this with the section cut, and so you basically want to make a cut just so that you can view it on the inside. There's a very quick and easy way that you can do that within ANSYS as well. Okay, and so with that, let me go ahead and share my my laptop screen. Okay. All right, and so I'm going to do all of these with the globe valve, just because that's the one I was kind of playing around with. But you can of course do this for for any other geometry as well. Okay, and so the first thing we're going to do is we're going to do point number one, which is the creation of a smaller surface for applying forces. Okay, and so the situation is kind of like this. And so let's say that you have this surface right here, right? Actually, maybe this one is probably easier. Okay, and so this, when you click on the surface, you kind of select the entire cylindrical part at the same time. Okay, and so for a lot of cases, that's fine. But let's say that you want to model a case where you have you have some kind of impact that hits it from the outside, right? And so you want to apply the boundary condition in, let's say, a tiny area like this, okay, and not affect the entire rest of the model. Okay, and so the way that you have to do that is you basically have to create another sketch to define that region, and then you're going to project that region onto the model. Okay, actually, let me see. Okay, that's a little better. Okay, just so now the whole thing isn't transparent. Okay. And so you have to do this in a few different steps. Okay. So the first thing you have to do is you have to draw your sketch, draw a sketch on the plane that you want. Okay. All right. And so there's a few ways that you can do this. And so, you know, one way that you can do is you can just simply click on the surface, and then you can go and then click on sketching down here. Okay. And so by highlighting surface and clicking sketching, what ANSYS is going to do is that it's going to create a sketching plane for you that's going to be tangent to this surface. Okay. And so if you can see from here, after I click sketching on there, then it created a new sketching plane that's right tangent to this surface. Okay. Right. And so if you go back into modeling back here, okay, you can see here that we have plane number 4. Okay. And this plane number 4 is, you know, coincident onto the surface right here. Okay. And so that's one way that you can create a sketching plane, is simply just to click on the surface of interest and then just click on sketching. Okay. But if you want to be a little bit more precise in terms of what plane that you want, then you can go ahead and create another plane. Okay. And so if you go to create right here, you can click on new plane. Okay. And so you can see here we've created a new plane right here. Right. And then from this new plane, what you can do is you can define, you know, first of all, the direction for the plane, right? And so one way you can do this is you can say that, you know, this plane is going to be parallel to one of the base planes here. Okay. And so let's just say for the, just for the sake of this tutorial, we're going to make a plane that's parallel to the YZ plane. Okay. So I'm going to highlight the YZ plane right here and then click apply. Okay. And so now this new plane is going to be parallel to that one. Okay. Right. And so right now it's actually exactly the same as the YZ plane. But let's say that we want to offset it by a certain amount. Okay. And so what you can do is you can go to transform 1 right here. Okay. And so transform 1 is going to let you, you know, either move the plane around or rotate it. And so let's say that we want to offset it in the X direction. Okay. Right. And so this is going to let us offset the plane in the X direction by an amount that we specify. Okay. And so let's say that, you know, we want to offset this amount by, let's say, 0.05 meters. Okay. Oh, I'm sorry. The X direction is that way. So actually, we want to offset this in Z. Right? So let's change this to, and so, you know, it's a little bit confusing because the planes have their own coordinate system here, but it's going to be different than the global coordinate system here. And so you kind of have to look at the colors of the arrows, right? And in this particular case, I want to move the plane, you know, out of plane up over here, just so that, you know, we can get it onto the surface of the cylindrical part, okay? And so I'm going to offset it in Z instead, okay? And you can see here that now it was a little bit hard to see, but now this plane is no longer at the center of this part. It's now offset to the side, okay? And if we want to get this closer, we can do this 0.04, okay? And you can see now that we're closer onto the surface, okay? And so your new plane doesn't have to be touching onto the surface itself, although it makes your projection look a little bit cleaner. And so the closer you can get the surface, the better. But just to illustrate to you that you don't have to have this plane perfectly connected to the surface, I'm going to leave this plane a little bit offset, right? And so can you guys see from from your computer screens how this plane right here is offset from the you know, from this one? Right. And so here's kind of the centroid of this plane right here, and I want to project a you know, I want to project a you know, a little circle onto this surface right here. And so you can see that the plane that I created was a little bit offset from that over here. Okay. Okay. And so now that we've created this this new plane, let's go ahead and sketch in it, right? And so you're going to go to the tree outline right here and click on the new plane that you just created, and then you're going to click on sketch. Okay. Right, and so now we can go ahead and create a sketch here. And so let me go ahead and center this up onto, so I'm looking right at the plane, okay? And I'm going to draw a circle on here, okay? Let's say that the circle is going to be just like this. Okay. All right. And then so we can go ahead and dimension this this circle. Okay. And so let's say that we want a diameter of 0.025, okay, meters. And then let's offset it from the bottom here. And so let's do one more dimension, and we'll do vertical. Okay. Oops. And so let's go ahead and do the vertical dimension with down here, or with this plane right here. Okay. Oh, sorry. Oops. Is this horizontal? Okay, it's horizontal. Okay. And so let's say that we want this to be 0.008. Okay. And so our circle is kind of moved up a little bit right there. And of course, you know, you can move this around as much as you need to, depending on where you want to apply the force. But in this case, I want to apply a force that's kind of striking on the outside right there with an area that looks like that. Okay. All right, and so this is our you know our location that we want to define. Okay, and now the next step is going to be to project this sketch onto the target surface right here. But we have to do that in a few different steps. Okay, and so the first thing we have to do is we have to create a we have to actually transform this sketch into a solid, because right now the sketch ANSYS doesn't really do anything with sketches, and so you actually need to turn it into a solid in order for it to do anything. And so we're actually going to do an extrude. Okay, and so with sketch 2 highlighted, we're going to click on extrude up here. Okay, so let's go ahead and click extrude. Okay, we're going to apply this onto sketch 2. Okay, and we want to extrude this a certain amount. The exact amount that we extrude doesn't really matter, because we're going to suppress this extra surface or this extra solid anyway. But you know, we have to do this in terms of we have to add what's called a frozen surface. Okay, and so a frozen surface is going to be differentiated from all the other parts in the model, because it's you know, all the other parts are considered solids, and the frozen ones are, you know, are basically make it so that, you know, this solid can't be modified at all by anything else. Okay? And so the exact amount that we extrude this doesn't really matter. You know, all we really want is just to create a solid. And so I'm going to go ahead and change this to 0.1. Okay. And so you can see that's going to create a cylinder that's extruded just like that. Okay. So I'm going to go ahead and click generate. Okay. And so you can see now that we've created a solid. Okay. Right. And now what we're going to do is we're going to take the bottom surface of this or the bottom edge of this solid here, and then project it onto our glow valve. Okay. All right. So we go ahead and clear this. Okay. And so to do that, you're going to go to create, and then you're going to click on. I'm sorry. You should go to tools right here, and you're going to go to projection. Okay. And so this is going to project whatever sketch that you have onto a surface, right? And so the way that you use this is you first define the edge of the sketch that you want to project. Okay, and so I'm going to click on the circle that I just created, and I'm going to hit OK. Okay, and so now our edges are defined, and then next we're going to define our solid, or the target for this. And so we're going to click on target right here. We're going to click on this cylinder part right here. We're going to hit apply, right? And then from there, we're just going to hit generate. Okay. And so what it's doing right now is ANSYS is taking that circular sketch and then projecting it onto the surface. Right? And so it's a little bit hard to see from here, but you can see that now when I click on this surface right here, then that part that we just projected onto it is no longer selected. And then we can select that part now as something different, right? And so now we've basically designated this area right here for us to apply a boundary condition, okay? All right. And so last thing you're going to want to do is because this cylinder right here is kind of a nuisance, and so we don't actually want this to be part of the model. And so, you know, it's served its purpose, and so it's basically allowed us to perform this projection. And so we can just suppress this this cylinder now. And so, you know, if you just created the new surface within ANSYS, it's going to be created as a solid right here. Okay. And so you're going to right-click solid, you're just going to suppress it, okay? And then all you're left with now is just your original geometry, but now you have a place that's cut out where you can apply a force, okay? Right. And so when you take this geometry into ANSYS Mechanical, it's going to it's going to remember this, and it's going to allow you to apply a boundary condition on this region right here. Okay. All right. Any questions on this? Okay. All right. And so I do have a handout for it, and so I haven't uploaded it yet, but I will upload it after the class today. And so that handout kind of goes over this exact process right here. Okay. All right. And so that's projection. Okay. And so that's how you create a another surface in your model for boundary conditions application. Okay. And so the next feature I want to go over is, let's say that we want to split this model in half, right? And so let's say that we notice that, maybe we've noticed that this entire cylinder, this entire globe right here is symmetrical across this direction, right? So it's a little bit easier if I see it in this one, right? And so if I draw a line right here, right? Imagine I drew that line a little bit better, a little bit centered. You can see that that our geometry is symmetric above and below the line, right? And so what a few people have been asking me is that, when you have symmetry like this, can you just perform the analysis on just one side of the model, and then have that be, and then just assume that you get the same results on the other side? And the answer is yes. And so you can actually do that. But in order to do that, you have to actually split the model, or you actually have to cut out a model, cut the model in half. Okay. And so there's several ways to do this. And so there's, literally several different ways you can cut the model. But this is kind of the easiest way that I like, or at least the one that's most intuitive. Okay. And so what we're going to do is that we're going to basically kind of do the same principle that we did last time, where we're going to basically split all the surfaces in half. Okay. And then all the parts that we kind of split along the halfway line, we're just going to suppress them. Okay. All right. So the first thing you want to do is you want to find a good cutting plane for your model. Okay. And so for this particular case, I want the YZ plane. Okay, because this is going to cut the model right in half in the way that I want. Okay. And so for this particular model, one of the default planes works really well. But if one of the default planes is not what you want in terms of splitting, you can create a new plane basically in the exact same way that we talked about earlier today. Okay. All right. And so what we want to do here is we're going to go, once we have this plane highlighted and we know we're going to split along the YZ plane, I'm going to go to create, and then you're going to go to slice. Okay. All right. And so under slice, it's going to ask you to select a plane on which you want to slice against. Okay. And so like we said before, we're going to slice along the YZ plane. Okay. And then your slice target is going to be all the bodies in the in this geometry. Okay. All right. And so with that, with the slice plane selected, we can go ahead and hit generate. Okay. And you can see now we have kind of like a Harvey Dent kind of a two-face kind of thing going on with our model. Yeah. Or question. So is there a reason I'm not using space claim, or is it just preference? Yeah. So so all the YouTube videos I saw today on this stuff use Design Modeler, and so I use the Design Modeler for that. Yeah. But also the projection thing that I just showed you, I actually do have a tutorial on that in Design Modeler, and so I thought I'd keep it consistent with that because I'll post the handout for that after the class today. And also switching programs is kind of a pain, and so that's why I kept everything in Design Modeler. Okay. Mm-hmm. Okay. And so now that we've kind of two-faced our geometry here, okay, you can see that one side of the geometry is distinct from the other one. Okay. And actually, if you open up the parts list, right, and so if you go to the tree outline here and you open up this part right here for 25 parts and 25 bodies, okay, right. And if you were paying attention, and if you kind of noticed, earlier in the lecture today, this only said, 20 parts and 20 bodies before, right? We have one extra body from the frozen surface that we created, but that's not important anymore, okay? But we've also created these extra, these new ones right here, which are the result of our split, okay? And so if we want to get rid of this part of the model, all we have to do is just right-click this and then suppress it, okay? And so this thing too, I don't even know where this is. This is this thing right here. Okay, so we can right click this, suppress it, right click this thing, suppress, right click this thing and suppress. Okay. And of course, for the globe valve here, we have, all these nuts and bolts. And so you're going to have to find out what those nuts and bolts are and suppress them too. Okay. And so let's see, nut, that one, not that one, that one, not that one, that one, not that one, that one, that one, that one. Okay. And also this one, and then probably the last three. Okay. Right. And so these nuts are no longer desired. And so we can go ahead and suppress these as well. Okay. And we've successfully cut our model in half. Right. And so what you can do now is you can bring this into ANSYS and you can just do your analysis on just one side of the model and just not have to worry about the other side. Okay. And then, in order to actually perform a symmetry condition, you can actually, you actually have to apply a symmetry boundary condition on here. Which I'll show you in just a second. But to show that, I have to jump out of design modeler and jump into mechanical. And so, are there any final questions on this before I jump into mechanical?
Yeah. So, Professor, if you just forget to put that symmetry condition on there, will the calculations just come out completely wrong?
Yeah. Yeah, or it has a strong potential to, because the whole idea with symmetry is that there's a whole other part of the model here. And so the symmetry condition, what it's going to do is that it's going to make it so that you don't have any deformation into the symmetry plane, right? Because if this, say like this edge right here or this surface deforms into the symmetry plane, then you no longer have symmetry, because you can't have that happen in the real part. And so what the symmetry condition is basically going to make sure is that you don't have any deformation or rotation into this plane. Yeah. Okay. All right. Yep. All right. So let's go ahead and close out of this and let's open up mechanical. Oops. That's the YouTube video I was watching. All right. And then once we're in mechanical, I can do the show off the last feature, which is section planes. But section planes is actually the easiest one to see. All right, and so here is our model. Okay, and so you can see here we have our little bullet hole that we created before, and so we can now apply a loading right there. Okay, that's going to be independent of everything else. Okay, and then we also have our slice plane right here too. Okay. Oh, one thing I should mention. So be careful if you're going to use symmetry in your model. You have to be careful on cases like this, right? Because remember, with symmetry, we're assuming that the other side of the model is exactly the same as what's here, right? And so if we apply a force right here, then what's implicitly going to be assumed is that we're applying another force on the other side of the model that we're not, that we're not showing. And so, be careful combining these things, because remember, symmetry, you assume that everything is basically an exact mirror. And so the geometry and the boundary conditions are mirrored as well. And so I didn't plan on covering symmetry just yet. I actually do have them as part of lecture notes for later in the semester. But I think, I know a lot of people have requested it, and I think for this project, I think it'll help save a lot of cost as well. So I think it's definitely a good idea for this project. Okay, and so symmetry conditions, right? And so in order for symmetry to work out, basically everywhere that we've cut, for the for the symmetry cut, we have to apply a boundary condition there. Okay, so we're going to right click and insert here. Okay, and then let's see, symmetry. Oh, it's not here. Okay, and so if you don't see a symmetry boundary condition, maybe it's just not in the student version. You can kind of create the symmetry boundary condition yourself. Okay, and so you're going to go to oh, I think this is it right here. Yep. Okay, and so what you're going to do is you're going to apply a frictionless support. Okay, and the frictionless support is going to be on the on all the cases. Okay, Because what this is going to do is it's going to prevent any kind of motion that's going to go into the plane, right? And so you want to allow motion that's in plane, right? And so you want to allow you basically want to allow the pipe here to expand out this way, okay? And so that's fine. But what you don't want is you don't want the deformation of the pipe to go in here, okay? And so if you read the description for frictionless support, okay, you can see here that frictionless support is that it inserts a frictionless face support to prevent one or more flat or curved surfaces from moving or deforming in the normal direction, okay? And so the normal direction here would be kind of outwards, just like this, okay? Either out of the plane or into the plane, okay? And so the frictionless support will prevent that from happening, okay? Another way that you can do this is you can simply just apply a displacement support, okay? And so displacement support, you're gonna basically prevent any displacement into that plane, but you're gonna leave the other two dimensions free. Yeah. All right, question. So does this apply to the housing as well? Like, would we need to add a support where we cut the shaft in half? Yes, absolutely. Yeah, anytime you make a symmetry cut, you have to apply this. This constraint there, because you're basically cutting the model in half, and so you want to make sure that you don't get any deformation or rotation into that plane. Okay. Right, and so the frictionless support should do that because it's going to prevent any kind of motion in that plane. But the other way that you can do it is that you can just apply a displacement support. Okay. And so I know that maybe they took it out, but I know that in previous versions of ANSYS, and it's been a while since I've seen it, they actually have a symmetry boundary condition here that you can actually apply. But it looks like they don't have it for this version. So probably likely they don't have it for your version too. And so if you don't have it, if you don't see it, you can just do a frictionless support, and then that's the same thing. And so the shaft can deform, and so the shaft can still deform where you cut it. It just can't deform into the plane on where into the plane on which you cut it. But it can move within the plane, right? And so let's say that you cut the shaft kind of like this, right? And so let's say that you have your shaft like this. Of course, you can't see freaking blue. Let me change this to red. Okay. And so let's say that you have your shaft like this, and you cut it this way, right? It's okay for the shaft to move, this direction and this direction. That's fine, right? And because all that motion is in the plane. But what's not good, and what you're not supposed to get, is you're not supposed to get any deformation in this direction or this direction. Okay, and that goes for anywhere on the slice point, because that basically violates the condition of symmetry. Yeah, yeah. And so doing this frictionless support will prevent that from happening. Yeah. Mm-hmm. Okay, and so that's how you split a model. And so if you want to use that for your project, I think it works really well for both the globe valve and also for the shaft housing. Okay, and so the last thing I want to show you is how to create a section plane. Okay, and so for here, there's kind of no point because we've already sliced the model, but I don't want to reset the model. Or actually, we can bring stuff back, or maybe not. Maybe it's gone. Okay, it's gone forever. But let's say that you have this entire tube surface here, and you want to look on the inside, right? And so on Monday we went over a technique called hide faces, where you can hide the outer surfaces of the model, so you can apply boundary conditions on the inside, right? But on Monday, so I want to ask if you can do a section plane, which is kind of like a temporary cut within the model, where you can kind of see what's going on the inside. Okay, and so you can do that from mechanical. Okay, and the place that you're going to go is you're going to go to home. Okay, and then you're going to go to section plane right here. Okay, all right, so you're going to click on section plane. Okay, section plane. Okay, and then your cursor is going to change to this icon right here, and so you can see that it's I have a mouse with kind of a half shaded box on each side. Okay, and then all you have to do from here is just to take your mouse and just make like Fruit Ninja and just slice the model in half. Okay, and then there is your section plane. Okay. If you want to modify the section plane, so let's say that you're not happy with this cut, you can go down to the bottom left of the screen. Okay. And you can see here that we have two options here for details and section planes. And so we're going to switch over to section planes right here. Okay. And you can see the section plane that I just created. And so if you click on this section plane right here, you can click on edit. Okay. And then after you click edit, you can see that we have this little bar that shows up in the model now. Okay. All right, and so you can use this bar to kind of modify the section plane as you want. So one thing that you can do is you can click on the box right here and you can move the section plane up and down. Okay, and so you can modify the region on which you're performing your section cut. Okay, and so same thing with this line right here. If you want to view the other side of the model, you can go ahead and click on this dotted line. Okay, and so the dotted line will have you switch between the two parts of the model that you're creating a section for. Okay. And so if you want to create a section plane on your model just to see, the interior of a certain part, or even you can do this for the results too. And so if you want to look at a section plane after you've run your simulation and you want to see what the stress is like kind of on interior cut, you can do that from the section plane right here. Okay. Okay, I think that's everything. So are there any questions on these three features here? Okay, all right. So hopefully that's helpful for you guys to help you do your project, right? And so either in terms of applying boundary conditions in a certain place, or maybe doing symmetry, or doing a section cut, right? So hopefully these are useful. All right, question. So is there a way to make a section cut parallel to a plane? Yes, I think there is. And so let me see here. New section plane rename. Yeah, I think there is, but I didn't get that far in the tutorial, and I had to do some other stuff today. But there is a way to basically bring up some more kind of advanced settings for this section plane, and you can actually define how the plane is actually defined in terms of in terms of different planes in the whether you want to be parallel to one of the principal planes, or if you want to modify the normal vector or the angle directly. So I did see that was part of it, but I just didn't get there to that part of the tutorial. But this will at least help you get started, and then you can kind of find that feature if you look it up online yourself. Yeah. But I know it's there. I just didn't get to it. Yeah. Okay. All right, so let me go ahead and bring it back here. All right, and so let's get back to talking about meshing again. All right. And so again, this set of lecture notes on advanced meshing is kind of like all the rest of the important information you should know about meshes, for you to use them in ANSYS. Okay. And so I think where we left off was, we were talking about specific meshing controls within ANSYS itself. Okay. Okay. And so last time we talked about how does the hex dominant method work, right? Okay. And so hex dominant is a method that I think everyone's been using quite a bit throughout the different activities. Okay. And remember, the goal for a hex dominant mesh is to create as many hexahedral elements in your mesh as possible. Okay. Okay. And the way it did this was it first created a mesh. And so what ANSYS is going to do first is that it's going to create a mesh of only tetrahedrals and triangles. Okay? Then once it does that, it's going to merge together neighboring tetrahedrals and neighboring triangles to form hexahedrals and quadrilaterals. Okay. Okay. And so, at least in the very first stage of the this meshing method, is that you're guaranteed to get a mesh, right? And so remember, whenever you create a tetrahedral mesh or a triangular mesh, you're always guaranteed to get a mesh out of that. Okay. But when ANSYS is going to go towards the fusing phase, right? That's when things can usually get messed up. And so if there are if the tetrahedrals are created in such a way that they're that they can't reasonably be fused and create a nice looking element, that's when things get tricky. Okay? And so ideally, it should look something like this. Right? And I'm going to draw the 2D version just because it's a little bit easier. Okay? Okay. And so ideally, you should have something like this, where you have your triangular elements, okay? And then when you fuse them together, you can basically just remove, some edges here, okay? And then here is your quadrilateral mesh, okay? And so this is something that was successfully fused. Unfortunately, you might get situations like this where, let's say that your triangular or tetrahedral mesh is really, really skewed. And so let's say that we have a situation like this, okay? So we have two triangular elements that are right next to each other, okay? And so if we try to remove this this edge right here, okay, right? Because that's the edge that's bordering between two different triangles, okay? And we try to form a quadrilateral from this, you can see that this quadrilateral is pretty scuffed, and so it's not the best looking quadrilateral. Okay? And in fact, because the way I drew this, because these these two edges right here are parallel, we actually end up with a triangle back again. Okay, and so in the cases where you get kind of a very skewed triangular mesh or a very skewed tetrahedral mesh for your particular geometry, those are situations where your hex dominant method is going to fail, because it's going to try to fuse elements like these together, and it's going to create a really wonky element which has skewness of like who knows what, right? Okay. Right, and so when the hex dominant method fails in ANSYS, probably something like this is happening, where it was able to create a triangular mesh or tetrahedral mesh, but actually performing the fusion here was not successful. Okay. All right. Any questions on this? Okay. All right. So that's hex dominant, and so hex dominant I think is the easiest way for users to create a hexahedral mesh, because they don't really have to do anything. All you have to do is just specify hex dominant, and then ANSYS will follow the rest. Okay. And so for some of these other methods, there is a default setting for it, but there's also some degree of you can modify it yourself in order to get it to get better results. Okay. All right. And so the next method for creating a hexahedral mesh is called the sweep method. Okay. And so you might have seen the sweep setting when you've been modifying your meshing settings in ANSYS. Okay. And so the idea with the sweep setting is that you basically are going to start by meshing one face in your model. Okay. Okay. And you're going to mesh that face with quadrilaterals, okay? And so ideally, it should be a face that's going to be relatively easy to mesh with quadrilaterals, okay? Then from there, you're going to take that face and then kind of sweep it along the rest of the body, and then along the way, creating a hexahedral mesh. Okay? Okay. And so the way it works is something like this. Okay? All right, so let's say that we have a square surface, okay? And square surfaces are great for quadrilaterals because they, you can kind of just basically put a waffle on this and we get a quadrilateral mesh, okay? And let's say that the rest of the body, looks something like this. Okay. All right, and so under the sweep method, let's say that we've chosen this face in the front as our starting point, okay? And so first thing we're going to do is we're going to mesh this guy with quadrilaterals, okay? Okay. Right. And then from here, once we've meshed our initial face with quadrilaterals, we're going to sweep it through the rest of the model. Okay, so we're going to take this and we're going to sweep this. Okay, and then along the way, we're just going to be naturally creating hexahedrals, right? Because we're basically taking this stencil right here and kind of sweeping it to sweeping that stencil through the rest of the body, and then kind of marking things off as we go. Okay. All right. And so the if you don't specify anything, I think ANSYS kind of it will choose your source, your initial surface by default. Just based on its characterization of the surface. Okay. But you can actually manually select this. Okay. And so this initial face, or the face where you're going to start your mesh, this is called the source face. And so this is something that you can manually change within your model itself, okay? And then all the faces that you're going to sweep towards, those are called your target faces. Okay. So remember, you're going to be sweeping from the source to the target face, okay? All right. Any questions on this?
Yeah, so Professor, a quick question. So if we have a face like that, like in a real geometry that's mostly square, that's well modeled by quadrilaterals, if we choose that as the source face, is it going to produce a higher quality mesh on the target faces, or does that matter?
It does, yeah. And so the whatever you choose as your source face, think of that as kind of like your stencil. And so basically, whatever kind of quadrilateral mesh you get on that source face, it's going to basically try to propagate that through the rest of your model. And so if you choose your source face to be something where you can get a good quadrilateral mesh on, then that nice mesh is going to propagate through the rest of your model. And so the rest of your mesh is going to look good as well. And so for geometries where you do have like a very nice source face and you can kind of see the sweeping, happen really nicely, then sweeps actually produce a pretty nice mesh for you compared to the other methods. Yeah.
Cool. Thank you.
Yeah. Mm-hmm. All right. And so that's sweeping. And so sweeping works great I would say for geometries where you can kind of imagine this happening. Okay. But unfortunately, a lot of geometries just aren't like that, right? And so if you think of the glow valve that you have for your project, right? And so that's a model where I think it would be hard to find a good sweep surface for that. Okay, even for the bearing housing too. So I think a sweep would work really well for the shaft itself because you basically just have one shaft that goes throughout. But if you're trying to mesh the housings, that's definitely going to be difficult for for the sweep method to do. Okay. And so another twist on the sweep method here is that, instead of just having one source and multiple targets, there's a variation on this where you can have multiple different sources and they kind of sweep up into a certain amount. Okay, and so that's called the multi-zone method. Okay. And so under the multi-zone method, basically this kind of works on the same principle as the sweep, but instead of just having one source, you can have multiple different sources. Okay. And so this works really well for more complicated geometries. Okay, and so just as a simple case right here, let's say that we have a like a Texas-looking geometry. Okay, or I guess you can say this looks like a cactus. Okay. Okay. And so under the multi-zone method, you can say that, okay, I have kind of a strange geometry, although I think for this one, actually regular sweep can work really well too. Okay. But what you can say instead is that, let's define these three surfaces right here. Those will be our sources. Okay. And then let's have them sweep over only a certain range. Okay. And so let's have the first surface maybe sweep along that range. We'll have the second surface sweep along that range. And we'll have the third surface sweep along that range. Okay. All right, and so under the multi-zone method, you kind of have all the benefits of the sweep, but you have kind of more degrees of freedom for you to modify the settings so that you can get a higher quality mesh. Okay. Okay. Any questions on this? Okay. All right, and so those are the settings that are available to you under when you choose hexahedrals for the element shape. Okay, and so there's different methods, and so if the hex dominant method doesn't work, you can try with sweeping and see if that works for you. Okay, let's talk about some of the options that you have available to you for tetrahedral meshes. Okay. And so again, this is these settings right here are I know several of you have come across them, and you've asked questions on it, and so I've kind of asked you guys to be patient about it so that we can discuss it together as a class. And here it is. Okay, and so two of the settings that you'll see in your tetrahedral meshing are patch conforming and patch independent. And so let's talk about what each of those settings mean. All right, so patch conforming. All right, and so remember, we're talking about tetrahedral meshes here, and so we're always guaranteed to get a mesh no matter what. Okay, and so these two settings right here, kind of, they're not anything that's going to make or break your geometry, but it's going to make a difference in how your mesh looks. Or in other words, or another way to think about it is it's going to affect the quality or the skewness of your elements. Okay. But it's also going to affect how your mesh models your geometry as well. Okay. All right, so let's start with patch conforming. And so patch conforming, you can kind of think of this as, you know, you're going to be building your mesh from the outside going in. Okay. And so in other words, what this method is going to do is that the first thing it's going to mesh, it's going to mesh all the exterior surfaces of the model. Okay. Okay. And since we're doing a tetrahedral mesh, we're going to be meshing them with triangles. Okay. Right. And so the good thing about this is that, you know, all of the exterior surfaces are going to be meshed perfectly. And so what that means is that, you know, the geometry or all the geometrical features of your model will be perfectly represented. Okay. Okay. And so no matter what, you know, strange or fine features that you have on the outside of your model, patch conforming is going to make sure all that is meshed perfectly. Okay. And then once all the exterior surfaces are meshed, then the mesh is kind of grown inward. And so then once the triangles on the outside are set, then the tetrahedrals on the inside are produced, you know, from based off growing from the outside. Okay. Okay. All right. And so, you know, this patch conforming method, I believe it's the default. It should be the default. And so I would say this is kind of the very, you know, if diving into kind of meshing theory a little bit, this is like the standard way to produce meshes. And so first thing you do is you mesh the exterior, you mesh the, you get a surface mesh, you know, as they call it. And then from the surface mesh, that defines how your volume mesh is going to develop. Okay. And so in a lot of the other softwares that I've used, a lot of the other research softwares, this is basically the only way to mesh stuff. Yeah, because a lot of times you want to prioritize that you capture all the geometric features that you can. Okay. Okay, and so that's how the patch conforming method works. Okay, and so what's the downside to this method? Okay, and so the downside to this method is that, you know, because it's so strict on making sure that you represent the geometry exactly, what can happen sometimes is that you're very likely to create some distorted or skewed elements. Okay. Or maybe I shouldn't say it creates it often, but it's much more likely to create these distorted elements, because with the you know, because you're prioritizing the geometry so much, then you know, basically, you know, if your geometry is doing some kind of weird things, then, you know, it's going to try its best to kind of fit the geometry, but it might have to produce like a very strange element in order to do so. Okay. And so that's not to say that it happens all the time, but I would say it's much more likely to happen versus patch independent, which is the method that we're going to go over next. Okay. But for cases where you want to, you want to make absolutely sure that you respect every geometrical feature, then patch conforming is the best way to do that. Okay. Any questions on this? Okay, and so let's go over patch independent. Okay. And so patch independent is the exact opposite process. Okay. And so instead of starting your mesh from the outside and going in, patch independent is going to go from the inside and go out. Okay. Or in other words, the first thing that's created is going to be all the tetrahedrals on the inside. Okay, and so it's going to start with filling the space with tetrahedrals. Okay. Then those tetrahedrals are grown in a way such that they move towards the exterior of the surface. Okay. Right, and so this process keeps continuing until the tetrahedrals kind of go beyond the boundary of the geometry. Okay. Then once the tetrahedrals grow beyond the exterior boundary, then what ANSYS will do is that it'll project those tetrahedrals onto the exterior surface. Okay. Okay. All right. And so what is this? What does this do? Okay. What this will do is that this is going to optimize for the quality and the shape of your elements. Okay. Okay. And so for patch independent, because the volume mesh or because of the tetrahedrals are created first, then ANSYS is going to make sure, or it's going to do its best to make sure that you have as many high quality elements as possible. Okay. And so this is great for situations where you're just getting really skewed elements and it's kind of screwing up your results. And so if you switch to a patch independent, then you're going to get a much higher quality mesh in general, at least in terms of the element shapes. Okay. All right. And so that's a big plus. The downside for this is that the geometrical the faithfulness to the geometry kind of takes a back seat to the the mesh quality. Okay. Okay. And so you might lose out on some geometrical features in your model because you're focused because the ANSYS is going to be focused a lot more on producing nice high quality elements. Okay. And so if you really care about all those geometrical features, then And that's more important to you than the mesh quality, then, make sure you use a patch conforming method versus patch independent. Okay. But I will say that, it might seem like a bad thing if you're losing geometrical features, but, I'll argue that, this is not always a bad thing. And so if ANSYS is going to automatically ignore some really fine features, probably what's likely is that those features probably weren't going to be that important anyway. Okay. Okay. Because a lot of the times, a lot of the features that you end up missing from patch independent are going to be like really tiny details on the surface, right? So little curvatures, or maybe little tiny, surface features, right? Or like an imprint on the surface. A lot of times, those tiny features are not going to add anything significant to the structure of the structure of whatever you're analyzing. Okay. Because most of the stiffness or most of the strength is going to come from the interior, right? And so those small features, most of the time they're most of the time they're going to be aesthetic features. And so if you ignore them, or if you kind of lose them, it's not that big a deal most of the time. But sometimes they are important. So one example I can think of the top of my head is tire treads. Okay. And so for tire treads, you have a lot of very fine features within the treads, right? But those treads, make a big difference on the performance of the tires, right? And so those are small features that you want to make sure you capture. And so if you do a finite element simulation of a tire, and you're missing out on those small features, then probably your simulation is not going to be that reliable or that accurate. Okay. And so it's at the end of the day, it's a judgment call. And so you have to kind of think about your geometry and think about what's the most important thing for this simulation. So is it going to be more important to get perfect geometrical accuracy, perfect geometrical faithfulness, or is it going to be more important to get high quality elements just to make sure that the results that you get are reliable and they're converged? Okay. Okay. Any questions on this stuff?
Yeah, Professor. I have a question about this. So I know last time you talked about how we have all our metrics to determine if our mesh is high quality.
Yep.
Like the mean was it okay here? So like the min and max skewness and then the mean skewness.
Yep. Mm-hmm.
So you're saying that this patch independent is going to be producing a high quality mesh, right?
Correct.
So if we were to just look at our mesh metrics, we would probably see that they are better than a patch conforming method. Would I be right to say that?
Yes. You're much more likely to do so. Yeah.
Okay. So how do we know, let's just say, we're going through our design process and we do our calculations with both, and our metrics are better for the patch independent method, but how would we know that the calculations are less accurate if it was to not correctly model some geometrical features because it's prioritizing the quality of the elements instead?
Yeah, no, it's a great question, and I think it's the $1 million question when you're considering meshing is, which things do you prioritize? And unfortunately there's no blanket statement, and there's no kind of truth that I can say that that's going to lean one way or the other, because it really depends on the situation. And so kind of what I would at least my general approach to meshing is that I almost always go for patch conforming first. And then I know that all the geometrical features are going to be preserved, because that's something I can control. Because with the patch independent, it's a little bit hard to control over what features are kept and which features are kind of kaput. But with the patch conforming method, I can run my simulation with that first, and then I can actually look at the results and see, I can actually zoom in on all those fine features, and I'm like, okay, am I actually getting some interesting behavior? So I'm actually getting some stress concentrations. Am I getting some high solution gradients around these fine features? And if I am, then probably that's a good indication for me that I should keep the patch conforming and maybe just work on refining that mesh as best as I can. And so work on mesh refinement instead. But if I'm if I run my patch conforming simulation and I see that I'm struggling with convergence, and so you can check convergence in the in ANSYS, and I think probably and then we're going to do that on the next activity actually that we're going to do next week. And I see that it's really struggling to get down there, and I see that probably the skewness might be a culprit. Then that might be a case where I switch to patch independent. And see if that helps me with my convergence. Yeah. So it's a case by case basis, and so it's really hard to say what's better one way or the other. Yeah.
Okay, thank you.
Yep. Mm-hmm.
Oh, sorry, one more thing.
Sure.
Can we just isolate, like if we have a geometry that we know is going to be particularly well modeled with triangles, can we just isolate that piece and then just do patch independent method there? So we would get like the highest quality solution there.
Absolutely,
it's going to be well modeled.
Absolutely, yeah. You can mix and match these settings as much as you want, and I think ANSYS does a really nice job of making that easy for you. And so you can select different parts of your geometry and say that this is a part where I want to do patch independent. Here I want to do hex dominant. That one I want to do patch conforming. And so you can definitely mix and match. Yeah. Mm-hmm.
All right, thank you.
Yep. Okay, and so we have about 10 minutes left, and we still have about a third of the notes left. And so, I don't think I'll finish the notes today, but I also don't want to pick this up next week, because next week is an ANSYS week, and we're covering actually something very different. And so we're covering dynamic simulations next week. And so my original plan for that week was to have kind of a like on Monday, we're going to do kind of like a quick introduction to dynamic simulation. So we'll have kind of a regular lecture on that. And then on Wednesday, we'll actually put that in action with an ANSYS activity. And so I want to kind of keep those two things coupled. And so, whatever we don't finish, we'll probably pick it up, the week after next one, when we have kind of a full lecture week like we did this week. Okay. And so the next thing I want to cover in terms of meshing is convergence behavior. Okay. All right, and so we've already gone over all the different element types, and so we've gone over all the different shapes that are available and all the different orders that are available, and we kind of talked about in general, how some are better than others for certain situations, but we didn't really quantify. And so what I want to do in this section right here is do kind of a lot of basically head-to-head comparisons between different element types, and show you just exactly how much better the convergence is for each one. Okay. All right. And so the data that I'm going to be presenting to you is this was all created from the same, very simple simulation. And so this was created from basically a simulation of a cantilever beam. Okay. Okay. And so geometrically it looks something like this. And so it's a 3D simulation. Okay. And so it's looks like this. And then we're applying a point load at the end. Okay. And then on the left side, it's fixed. Okay. And so for all the figures that I'm going to be showing you, basically they all did the same thing. And so they kept the boundary conditions the same. They kept the for each particular curve, they kept the element shape and order the same. But then what we did for each one was that they performed a mesh convergence test. Okay. Okay. And the results from this are presented basically in pairs. And so basically you're going to see the pairs of the results of their mesh convergence test. Okay. All right. And so the first thing we're going to compare, excuse me, is the linear tetrahedra versus the linear hexahedra. Okay. All right. And so, we've already talked about mesh convergence tests in activity 4. And so I'm not going to go over kind of the idea from them again. Okay. But remember, they're basically plots that look like this. And so on the x-axis, we have number of elements. Okay. And on the y-axis, we have the result for some quantity of interest. Okay. And for all of these cantilever beam simulations, the quantity that we're going to be looking at is the deflection of the tip. Okay. You have to do this for activity 4. Yes, correct. Yes, you have to do this for activity 4. Mm-hmm. Okay. And so, I should have done this in different colors actually. So let's say that the linear tetrahedra will be in red, and the linear hexahedra will be in blue. Okay. All right. And so for this particular simulation, the converged result, okay, or I would say the true result for the tip deflection is around 0.7. I think it's millimeters. Okay, and so the simulation will be considered converged once the deflection is computed to be 0.7. Okay. All right. So let's do the linear tetrahedra first. And so the linear tetrahedra is kind of the worst element that you can pick for this. Okay. And so actually, for small number of elements, it dramatically underestimates the tip deflection. Okay. And so it's so bad that it actually starts at 0.3. Okay. So that you can see that's less than half. Okay. And the convergence looks something like this. And so if we start here, the convergence kind of looks something like that. So actually, even for a really high number of elements, it actually never really fully reaches the converged value. So there's almost always a gap. Okay. And it takes so long to get there that the number of elements has to be something insane in order for you to reach convergence. Okay. All right, and so now let's look at the linear hexahedra, and really this is kind of not really a fair comparison, because the linear hexahedra, it doesn't converge right away, but it also doesn't start nearly as bad as the linear tetrahedra. And so, if you actually graph them next to each other, it almost looks like the linear hexahedra is a straight line, but I'll exaggerate kind of the beginning of the graph just to make it clear that it is actually starting something, right? And so for the linear hexahedra, it starts something like right here. Okay. And then it reaches convergence basically right away. Okay. Okay. And so there's a huge difference here between the linear tetrahedra and the linear hexahedra. Okay. 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 And so this kind of shows you just how bad the linear tetrahedra are at doing structural simulations. Okay, and remember, the main reason why we have such a big discrepancy is that linear tetrahedra are very susceptible to shear locking. Okay. Okay. And so you can kind of see that clearly in action here. And so for a very small number of elements, the linear tetrahedra elements are literally kind of locking up on itself, and it's just not able to deform nearly as much as it can. Okay. All right. And so this is kind of further evidence to kind of show that if you're going to be doing a structural simulation, then linear tetrahedra are just not the way to go. Okay. All right. Any questions on this? Okay, all right. So very quickly, let me go ahead and draw the graph for the quadratic tetrahedra versus the quadratic hex. And so just like before, Let's draw the tetrahedral in red and the hexahedral in blue. Okay. Right, and so just like before, we have the converge value here. Okay. And oh, sorry, the converge value is actually 0.75 millimeters. Okay. And so this one, this one is not that bad, honestly. And this kind of gives you faith that if you're doing a quadratic tetrahedra, you're actually in pretty good shape. Okay. And so the quadratic tetrahedra, it looks something like this. Okay. And so it might look bad, but actually, the place where it's starting from is actually already really close. Okay. Okay. And so if you compare this to the starting point for the linear tetrahedra is starting out at 0.3, which is way, way off, right? But for the quadratic tet, we're not at the converged value exactly, but we're starting really, really close. And so we're starting at 0.74 millimeters, which is, pretty much right there, okay? And then eventually you do reach the converged value. And so for the quadratic hex, of course, it's going to perform a little better, but not significantly so, okay? Right, and so you do get a little bit better behavior with the quadratic hex, but quadratic tets, like I've been saying, is totally fine. And so you definitely get really good convergence behavior for that. Okay. All right, any final questions on this before we wrap up for the week? Okay. All right, and so that's all we got time for. And so not next week, but the week after that, we'll pick up these notes and finish them up. Okay, but next week we're going to be talking all about transient simulation. Okay, and so I think the activity next week is one of my favorite ones, and so hopefully you guys enjoy it too, right? And so enjoy the rest of your and so hope everyone has a good weekend. Hope everyone enjoys the rest of their evening, and I will see you next week.
Have a great weekend, Professor. Bye bye.
Thanks, you too. Thanks, Jacob. See you next week.
Professor?
Yep.
I was just curious if you know how to use Patran.
I do not, because I don't know what that is.
Oh, it's a different finite element analysis.
Okay. Yeah, I can't say I've used it, but probably there's a lot of similarities in terms of how it's set up, or at least all finite element softwares, they do follow the same process. It's just the buttons are somewhat different and they call things different.
Yeah, that's what I'm having trouble with.
Yeah, that's always the hard thing about using a new software. But are there any online resources that like any YouTube videos or online tutorials that that kind of walk you through that stuff?
I haven't looked. I thought I would ask you first.
Okay. Yeah. Hopefully there's stuff on nowadays. There's a lot of resources you can find online for that stuff. So probably the audience may not be as big as ANSYS, or maybe it is. I don't know. And so because I feel like every year there's like, I find out about a new software that they're using in industry that I've never heard of before, but like millions of people use it apparently. So maybe it does have a big audience out there, and people post stuff about it online.
Okay, I'll take a look then. Thank you.
Okay. Yep. Mm-hmm. Kamal, did you have any other questions?
Oh, no, sorry. I was just sitting around like working on the activity.
Okay. Okay. I'm going to close the call then. I'll see you next week.
Yeah. Have a good one.
You too.